Alright, hell yeah, 10 minutes on the clock. I'm going to go over torsion, how I would do it. So I'm going to draw a little triangle here, and I'm going to say this is phi. So this is going to be the angle of twist. Let's make our arc there. And then I'm going to start my cylinder, that's going to be the starting portion of my cylinder. When we torque it, it's going to get that angle. This angle is going to be gamma. Hell yeah. And then we're going to have this length, that's going to be the length of our cylinder. Or circular bar. And so that's kind of the shape of it. We're going to use similar triangles. I'm going to say radians times radius is arc length. So this is the angle in radians. This is the radius. That's that arc length. Sometimes I like to put a little c here just to know, like, hey, this times this is little c. And then come over here. Radians times radius is this arc length. Okay, so this times this is little c. So now we can put them together. So we have these two multiplied are equal to those two. That's kind of the similar triangles, and we don't need sines because of the small angles. Probably this one you don't need sines because of the small angles. This is just the arc length of that. Or maybe there is no small angle approximation here. We got to move on. Hell yeah. And then so what we know about this angle is that this is the angle of shear. So on this little thing we have a square, and now it became a diamond shape, and we know that the angle is proportional to the shear with Hooke's law. Hooke's law say the shear stress with capital G, shear modulus of elasticity, times gamma, the angle in radians. So hell yeah. So I'm going to rearrange for this, and we're going to have the shear divided by the shear modulus. So we're going to insert that right there. So we have this angle of twist, radius is equal to the shear divided by the shear modulus times L. Hell yeah. And now we're essentially done. We just need to rearrange this. But this is our equation. We haven't done any integration, and we have an equation for angle of twist and the shear that we would experience on the surface. And the other thing, though, is this is going to be on the surface, so this tau is tau max. So let's write it out. We have this, and let's get this r downstairs. So we have tau max, L, G downstairs, R downstairs. Hell yeah. And what we know is that twist rate is just this divided by L. So we would have tau max, the L would go underneath there and make this, and then we would have GR. Let's solve this for tau max, and so we're going to have tau max is equal to, and they're going to do it like this, G, this angle R divided by L, or tau max is equal to, they're going to put the G first, the twist rate second, and then the radius. But these two equations are pre-integration. Hell yeah. And we're doing pretty good. I bet you we can do this. So now the whole idea of this is we applied a torque, a given torque that made an angle that created a shear. Because of these two triangles, these two values have to be the same. The rate of twist and then the shear on the surface. But if I want to relate, I don't know what the torque that I applied is. I just know that if I apply the torque, due to geometry, this comes out. So now we're going to say if I have a torque, I have to integrate. And we're going to do this cross-section where we have a small little chunk of dA, and it's a radius rho away from the center. And so we need to integrate from 0 to r, and then we need to go around 2 pi. And so we have to integrate, and we have to know what this value of shear is at any point along here. So this is shear as a function of rho. We know what it is on the surface, that's max. And so for shortness of time, I'm just going to say, well, hey, it's rho divided by r, it's the proportion times T max. And so that's the first equation that we use. And then so if I want to integrate, and what do I want tension as? I can do two things. I can get tension as a function of the max shear on the surface, or I can get, not the tension, but the torque. I can get the torque as a function also of the twist rate or, you know, the angle of twist. So that's what we're doing by integrating. And in this, and then when we do integrate this, well, if I do have a little shear multiplied by the area, these two multiplied is a d force, and then a distance of theta, a distance of rho, that's a d torque. So if I know a little piece of d torque, so I can integrate that little d torque, which is the integration of tau dA rho. And in this case, this tau is just rho r dA rho. And this is where they're going to be like, whoa, look at this. This is rho squared dA. I'm sorry, we have a T max in there. So, you know what I mean? I'm inserting this into there. So we have a T max divided by R, and then we have rho squared dA. That's when that integrates, this is a constant, you just get IP, and then you get T max divided by R. But I do not like to do it this way, but I'm okay with that. When we throw in this, cool. What's our function? So we're going to do this. We're going to do tau dA rho. Our tau term, well, this is our T max. So, you know what I mean? Our tau term is rho divided by R T max. So you can do it like this, but then you can have to insert this G theta R in here. So we have rho G theta R divided by R. The R's cancel. This is this part. We have the dA and then the rho. So cool, we have rho squared dA, and then we just have this as a constant. After integration, we just get G twist rate, polar moment of inertia. Hell yeah. But with this last 3 minutes, you know what I mean? I think that sucks. I think, you know what I mean? We're just going to try to slow it down for the last 3 minutes just a little bit. Probably not, though. When we do integrate this, we're going to have a tau dA rho. You know what I mean? From that. And so this is going to be rho r T max. dA, though, I guess I don't have too much time to go into it, but it's a rho d theta rho. You know what I mean? So cool. This is what I do. I got 3 rhos. When we integrate with respect to rho, we get 1/4 rho to the 4th from 0 to r. That's going to be r to the 4th divided by this. We're going to get r to the 3rd T max. The d theta integrates to 2 pi. And you know what I mean? And we just get pi T max r cubed divided by 2. So this is the tension T max. And it's just it's useful to always do the integration just so you're, you know what I mean? You're not maybe cutting corners and stuff and just using equations. So this one, same thing, tau dA rho. The tau is going to be rho r T max dA rho. The T max is going to be rho r. The T max is G theta r dA rho. And then we can go rho r G theta r. And this is rho d. Oh, do we even have time? I want to do this all in one clip. But what you're going to get is, no, it's going to work. It's going to cancel. And then, so hell yeah. And then you have r, and then you got rho d theta. And then the r's cancel, and you can have 1, 2, 3. In this case, you are going to integrate 1/4 r to the 4th, 2 pi, and then g, that, and we have 1 more minute. So hell yeah. So this simplifies to pi divided by 2, g theta for twist rate, r to the 4th. So now we have our 2 equations. And this is for the torque. And they're the same. You know what I mean? We, just like we said, you know what I mean? We apply some torque and both those things happen. So if we equivocate these, well, those are equal. Those drop out. All 3 of those drop out, leaving 1 of this. And we're left with T max is equal to G theta R, which is what we were able to do before integrating. So hell yeah. So under 10 minutes, it was just kind of interesting, you know, trying to do 2-hour videos and then trying to do something too fast. I think there's a balance here, you know what I mean? But I do like my 2-hour videos, and it's just fun to kind of like play around with 10-minute videos. But hell yeah. So thanks for joining me, and that's a video.